As Sherlock Holmes suggests, uh, we just don't keep something that we don't need, and we keep something only what we really need. But at the same time, we should have uh, the same speed or the complexity. Our data structure should be the same fast. Okay. For this reason, we use hash table data structure. What is a hash? Let us discuss it firstly. The hash function is some function such that um, number of possible arguments access much larger than the number of possible results of this function. Wise. Yeah. For example, if x from 0 to 10 to the 18, what can be the hash function? Hash function can be um, the last two digits of our number. So in that case, the result can be from 0 to 99. It's much smaller range comparing to range for arguments. So, for example, if we invoke hash function for 245, the result is 45. For very large numbers, also we get this 82 result. Um, so what we do now, if we consider this mm, hash function, we consider only Boolean array for all possible hash values of our hash function that is just 100. And what we do when we want to add element, we just compute hash value and use it as an index of our array. So the same for where we add true. For this element, we check existence of element, we remove it, and so on. So what we have much better memory complexity that is just O from M. And if M is very small, we have very good memory complexity with same time complexity. We solve the issue that we have with memory. It is about just 100 bytes, not 10 to the 18 bytes here. But what if we have two values with the same hash value? So, for example, 234 have 34 hash value, and 6834 also have 34 um, hash value. This means that if we put to our set number 234 and check, for example, existence of 6834, then our data structure says yes, we have such number, but in fact we put 234. So this situation called collision, and it is very, very bad situation. We should solve this issue too. How we fix this issue? If we consider our set, our bag, we can say that some numbers, some objects in our bag have one hash value, another objects have second hash value, and so on. For example, we have hash value 1, 0, 2, 10, and 5. What we do, we have this array with possible these indexes, possible hash value, and we put all elements of our set uh, to this index here. We put all this part here. We put all this part here, and so on. It is like we split our big bag to several small bags and put it to the elements of our array with indexes, that is hash value. We don't have just true false exists of some value from with hash value too. Um, uh, is existence of some value with value 5. But we keep all these elements as an additional bag. So how we can implement these bags? In fact, this part of our set is like a characteristic vector that we discussed before we improve this one. We use this implementation, but we have another implementation that is list. We can implement these bags as a list, and this hash table is like mix of two implementations. First of them is list, and second one is characteristic vector. So, in fact, we have array such that element of our array is list of objects. Size of array is m, where m is number of possible hash values. And what we do, if we want to add element, we get list by hash value of x and add element to this list. And if we want to check existence, we take a list by hash value and check existence element in this list, and removing the same taking list by hash value and remove element from this list. And we also um, consider s and keep it actual and decrease it if we add element if and it doesn't exist before, and we remove element and it exists before, so we keep as actual and just return s. What about time complexity and memory complexity? In fact, computing hash typically is constant time. Getting list by hash value is constant time, but adding element to list, removing element, checking existence that were discussed before with list implementation is complexity is max list size. So, or uh, if we have different size of lists, so if it is array implementation, we have maximal size of array, but or if we have list implementation, it is just size of list. And if we have several different lists with different lengths, so time complexity is max of these length sizes. And memory is m plus n, where m is number of possible hash values, plus n is sum of lengths of all lists. If we use, for example, array with changeable size, or we use linked list for implementation, in that case, memory is just n. It is sum of all lists, and what is the sum of all lists? It is the size of our set. It is total number of elements, because uh, we just split our existing bag to small bags and put it to these indexes. And some bags doesn't have any size, so they are empty if there are not some values with this hash value. Okay, let us discuss what should be hash function and what should be the number m, such that it enough fast, because we have this time complexity, and it doesn't take too much memory. Okay, the good hash or good hash function is the function that minimize number of collisions. If m is very big, such big as all possible values of arguments, then then we have definitely don't have any collisions. But we need small memory. That's why we want to minimize also this m value. But anyway, we don't need too much collisions. So firstly, we should have m bigger than n, because if we have n smaller than n by pigeonhole principle, we have collisions anyway. So it is like we have the several pigeonholes. It is m, and we have values that are pigeons. They each of them comes to some pigeonhole. So here, 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 and if number of these pigeonholes less than number of pigeons, then anyway we have at least two birds in one place. It means that we have collision. So that's why we need at least this condition m grades n. Okay. In that case, if m grades n, time complexity can be from constant time to up to linear. We have constant time if um, each list with each small bags for each hash value is very small, constant size. We just put two, three, four elements to one small bag. So we have uh, a few number of collisions. But if all elements have the same hash value and we put all of them to one small bag, this bag becomes big one, and we have linear time complexity because we implement it as a list, these small bags. Okay. In fact, if we have good hash functions that are used in implemented data structure in most popular many popular languages, then we have constant time in average. So in real value data, we have constant time for adding and removing. But if we have attack and someone knows hash function, and in fact, these hash functions are known for standard implementations, then someone can attack you and give you values such that all of them have the same hash value, and the time can be up to out from m linear. But in fact, in real world values, if we don't have such attack, then we can consider that uh, time is constant. Okay, what about memory? As we discussed, memory is n plus m, and typically for standard implementations, people use m like some constant times n. For example, m is 3n. In that case, we have memory that is 4n, that is anyway asymptotically O from n, because constant is hidden here in O notation. So we have memory, linear memory, we have constant time, everything is good, everything, we are happy. And we can implement dictionary or map data structure using the same idea. What is the map or dictionary data structure? So it is like map is mapping from one set to another set. It is like dictionary. It is like we have translation from one language to another language. And for example, I don't know, English and French languages. So we have English word and French translation of this word. or we say that it is like associative array. It is like array where indexes is not all indexes from in some range from 0 to 100, for example, but only indexes that we already assigned, which can be indexes only 0 and 100. So in that case, the memory that we use only for these two values, not for all possible values. So in fact, it is um, some collection of pairs key value. Key is like index in our array. Value is value that we put it. If we consider dictionary, key is like English word and value is French translation. Corresponding and mapping, it is mapping, it is like function. Key is argument of this function and the value is corresponding value when we um, find this function or mapping not for all possible keys, all possible arguments, but for only some of them. So the map is a collection of these pairs key value, or we can say the set of pairs of key value. In fact, how we implement it, we implement set of key values or for keys, set of keys. So we have back and we have both where key is written, for example, 5, yeah, that is key. But additionally to this ball, we write something additional, f, some value. So it is like for ball, it is set by key, but additionally we add something. We put some additional paper with this value, yeah, some value, and when we take ball with some specific key, we look to this additional paper that is uh, put it to this ball and, say that this is the value. Yeah? And what we do with such data structure, we can add some element with a specific key x. So we add um, element with key x and additional value y. We get value by key x and we remove some specific key. So we remove this ball. They are the same actions as for set, and we check size of them. For if we try to remove or get elements, uh, if there is no such balls, then we have different behavior in different languages. In some languages, like C++, we get 0 here value, some value. Here, when we remove, we something nothing, but do nothing. But for example, in Java, we get null value. In Python, we have exception here. That's why we should um, check existence of value before maybe to be sure that behavior is correct. Okay. And how we implement it, we just have list array where each element is list with per key value. And when we add, we find this pair by in key x and update value if it exists. If not, we just add this pair. When we get element, we search a pair x value by key x and return this in the element which we compute by hash for key and return the value. And for removing, we also compute index by um, key by hash and find in the list the pair by key and remove the whole pair. Okay, but anyway, we have this issue with possible attack with possible um, very slow and implementation, very big time complexity. And we try to fix it in next video.